Greetings. Our team number is 57-4 and our team name is D. We are studying in PSG College of Technology. As part of Phase 1A of Analog Design Contest, we are tasked with studying a function generator that produces square and triangular waves. We were asked to derive expressions for time period of square and triangular waves and also to measure peak-to-peak amplitudes of the same. This video will cover hardware implementation and simulation. This is our lab setup. We have built the function generator circuit using the ASLK kit, as you can see. The ASLK kit is supplied with the DC power supply of plus 10 volts and minus 10 volts, as you can see. We have used op-amp IC4 because it offers both inverting and non-inverting configurations suitable for our circuit. Now let us see the circuit we are about to implement. You can see the circuit we are about to implement. This is the non-inverting integrator and this is the Schmitt trigger. We are about to measure the node voltages VO2 and VO1. We have used source 1 of the CRO to measure the triangular wave. We have used source 2 of the CRO to measure the square wave, as shown. The parameters that we are getting in our output are: the frequency of the triangular wave is obtained to be 1.19 kHz. The frequency of the square wave is obtained to be 1.119 kHz. The peak-to-peak amplitude of the triangular wave is 9.5 volts and the peak-to-peak amplitude of the square wave is 13.8 volts. Now let us see the simulation we have performed in TINA. This is the connection diagram. This diagram mirrors our hardware implementation. As you can see, we have provided 10 volt supply as we have given the hardware implementation. Now let us see the output waveforms that we were able to generate. This waveform comprises both of the square wave and the triangular wave. You are able to see the parameters that we can study which would tell us about the square wave. The time period is obtained to be 872 microseconds and the peak-to-peak amplitude is obtained to be 16.91 volts. Now let us study the characteristics of the triangular wave. The time period of the triangular wave is obtained to be 864.36 microseconds and the peak-to-peak amplitude is obtained to be 11.62 volts. As you can see, the waveforms correspond in both the hardware implementation and the simulation, but there is a slight deviation in peak-to-peak amplitudes. Now we have done a slight modification to our function generator circuit to make it function as a VCO. The change we have included is, we have included an analog multiplier in the feedback path between the Schmitt trigger and the non-inverting integrator. We are providing the control voltage VC as shown here. Now the same circuit we have built using the ASLK kit, which you are about to see now. This is the circuit which we have built in the ASLK kit, and we can vary the control voltage in this DC power supply as shown. You can see the DC control voltage is 2 volts right now. We can adjust it to values like these to measure the changes in the graph. Now let us see the plot which we have obtained. Now let us consider the parameters that we were able to obtain. The peak-to-peak values of the triangular wave is obtained to be 11.6 volts. The peak-to-peak value of the square wave is 16.9 volts. Simulation part of this circuit. Again, we have used TINA to simulate this VCO circuit. This is the analog multiplier, as you can see, and simulating the circuit, you can see the transient graph as shown now. Now you can see that the time period that we are able to get for the square wave is 4.36 milliseconds, and the peak-to-peak value is 16.94 volts, which is exactly the same as we have got in the CRO. Now let's talk about the challenges that we faced during the implementation of these circuits. While implementing this circuit in hardware, we didn't have much of a difficulty. This is mainly because of the easy learning curve of the ASLK kit. And also the ASLK kit has a good prototype that favors easier handling. The main difficulty we had during the software simulation. Initially we had some trouble finding this analog multiplier, but later we were able to get this. And I would like to add that the ASLK kit was a great kit to work with. It's a great tool for beginners to understand analog systems modeling, and it's very user friendly. We were able to implement our circuit much easily with this ASLK kit. And thank you very much for your patience.